So we now begin with section 9 of LNL's classical mechanics. This section is titled Angular Momentum. And Landau begins this section by saying, let us now derive the conservation law which follows from the isotropy of space. Now, isotropy means that the mechanical properties of a system do not vary when it is rotated as a whole in any manner in space. So, isotropy means that mechanical properties do not vary upon rotation. And he does this, and well, he proves this by using a vector del phi as a infinitesimal rotation. And its magnitude is just del phi. I'm going to go ahead and note this as a vector, and just to be able to tell the difference when I'm stating magnitude or vector. And first of all, we find the resulting increment in the radius vector from an origin on the axis to any particle in the system undergoing rotation. So if we have our system, I'm going to note this as the vector del phi. This will be our radial vector, r. And here we have our new position upon taking the cross product, where r moves to. And we can tell that it has moved at this distance corresponding to this right triangle here. So if we define this change, the change in r, as del phi cross r, we know that if this r were to represent our position vector, it would shift due to the cross product, but the same would also happen with our velocities. So if we plug this in to the formula which is needed to state that the Lagrangian remains unchanged, we would get and this formula del L del R plus del L del V must still be equal to 0. And we know from previous chapters that del L del R is equivalent to the force acting on the 8th particle. And this is also equivalent to the rate of change of momentum. And we know that if we take the partial derivative of the Lagrangian with respect to velocity, we just get momentum. So if we plug these in here, we have p dot, and our del r is equal to del phi cross r. So del phi cross r plus p del phi cross v. And since we're working with multiple systems, not multiple systems, multiple particles, I'm going to write this all as a sum, and we can now take our del phi outside of the sum. So we have the sum over A times del phi multiplied by P dot cross R plus P cross V. And we notice that for this to remain unchanged, it must still be equal to 0. So we also have d dt of R A cross P, A all being summed over A, and our del phi is still remaining on the outside. Now if this term still equals 0, that also indicates that this term RA cross PA is constant. Now if we remember the term for angular momentum in basic mechanics courses, angular momentum is defined as R cross P. Thus, angular momentum is constant in time. Now, we can also do this with multiple frames. So, if I have a frame K and K prime, where in frame K, our radius vector is R plus some change. I'm going to call that A. And in K prime, I would have just R. So applying this to the previous formula, I would have that angular momentum is equal to the sum over A of R cross P, which upon expansion in the two frames would give me the sum over A of R prime A cross PA plus A cross the sum over A PA. And this term here can just be written as M prime plus A cross sum over A PA, which would indicate that the only way that this is constant is if our P, our whole system, or the momentum for our whole system is 0. So this is telling us that angular momentum depends on the choice of origin unless the system is at rest as a whole. So M depends on origin unless the system is at rest. Now, the same can be done for velocities. If I have two frames, again, I'm going to call them K and K prime, and in K prime, my velocity is just going to be V, and in K, my velocity is going to be equal to V plus V1. Now, if we take the angular momentum of a system and we substitute in our values for the changed velocity, we would get that this is equal to M r cross p plus m r cross, not p, my bad, r cross v plus mr cross v1. And again, this is just our regular angular momentum plus our mass of the whole system times the cross product of the velocity of the system as a whole. Because v1 would just represent the difference in velocities from one system to another.